Hey, what's up, guys? So, in this video, we're going to be going over my voice AI tech stack and the overall architecture. So, this is built for a service based business, specifically a home service business. This is the architecture that's going to be good for most use cases that a service based business would have. So, we have speech to text, state management, LLM, text to speech. Now, for me, speech to text, I'm using DeepGram Nova 3. I think this is one of the industry standards, and DeepGram is really good. Nova 3 is default on Pipecat, which is what I built my agent on, and I did custom code mine. So we have that for the speech to text, and then moving on to the state manager. So this is essentially to minimize hallucinations. So you could just have a monolith prompt and just put everything in it. So in one prompt, you just put greeting, qualification, scheduling, booking, and so on and so forth. Now, the issue with that is that you're giving way too much context to the LLM when it might not even need it. So if you're in the qualifying stage, you might not need the guardrails and tools needed for booking an appointment because you haven't made it that far yet. So this is what this is for. So for my agent, this state manager is comprised of both prompts and code. So I have different prompts. We have a greeting prompt, then we have scheduling, we have booking, we have completed, we have a transfer phase, which is if someone requests to speak to a human. So those are like the different states you want to have, and each prompt is super focused. It only has the context and rules for that specific phase, and then also it has the tools, or it has the context of the tools needed for that specific phase. So for example, the scheduling phase, you don't need the book appointment tool in that phase because you're just dealing with fetching times and confirming times. And then when you move on to booking, that's when you would need the extra context. So that's what that is. We have the LLM. I'm using GPT 5.4, and this was a really recent change for me. So if you watch my previous video, you'll see the improvements that GPT 5.4 had for me. And then the text to speech. Now, I know a lot of people use 11 Labs. 11 Labs does sound more natural, but Cartesia is faster, and I'm using Sonic 3.5. And with things like with booking appointments, I think Cartesia sounds natural enough, and then it's also fast. And that slight robotic nature, I think, is good for collecting and confirming contact info, so name, phone, email, address, those type of things. So I think for home service businesses specifically, I think Cartesia wins in this scenario. So that is the core structure of my voice agent. So now we're going to zoom out a bit. All right, so getting a little bit more advanced. So the 4 blocks here, really even the 3 blocks excluding state manager, that's like the most basic agent architecture you could have. Then the state manager obviously helps a lot, helps it to minimize the context needed for the LLM to serve its purpose in whatever phase it's in. But then you want to start adding more stuff just to make it more well-rounded and give it more capabilities. So that's where these two come in. So we have embeddings and RAG. So essentially, embeddings are just vectorized text. So let me just write down an example. Okay, so essentially what an embedding is if we were to vectorize, and what I mean by vectorize is essentially just translate this text. Oh, don't want to do that. Translate this text into a set of numbers essentially. And the reason why we want to do that is so we can allow the agent to actually understand what's being said, like the situation it's in, context, that sort of thing. So we know apples and oranges, they're both, and now I'm not going to get too deep into this, but this is just like a really high level example. So apples and oranges, they're both fruits. So that means their vectors or their set of numbers would be pretty close in range. So if we have a vector of apple, you give that to the LLM, and then you give the orange vector to the LLM. LLM will be able to understand these two things are similar in some sense. Now, if you put chicken, the vectors are going to be farther apart, or the set of numbers, the difference between the two are going to be farther, but they still fall under the food or edible category. So still kind of related, but not as closely related. So that's an example. So now for our use case for home service business, let's say we are building an agent for a roofing company. We want to have this vector stored. So this is pretty much something that will go in the FAQ section. This is a common question that someone might have. So we want to have a golden answer for whenever someone asks either this question or something very similar to it. So we would have a vector stored in our vector store, which is Qdrant. So RAG stands for Retrieval Augmented Generation. So this is essentially pooling the embeddings from our database. And database I'm using is Qdrant, which is a vector store. It stores embeddings. So we want to have a predetermined answer for common questions like how much is a roof replacement. So we would embed this and store it in our database. So whenever someone asks either this verbatim, how much is a roof replacement, or how much would a roof replacement cost, slightly different word wise, but the vectors will be close enough to where we'll get a hit. And then our LLM will be able to pull the answer from our vector store. So things like this, you want to have embeddings for frequently asked questions. So do you take insurance? What type of roofs do you guys service? What other services do you have? Like, do you offer hours, that sort of stuff? So that's where RAG and embeddings come into play for our voice agent. This is another thing that can help minimize context, which ultimately means minimizing hallucinations. So we never want to overload our agent or our LLM. So that's why we have the state manager. So we're not pushing too much context from the prompt into the LLM. And then we have embeddings, which essentially after every turn or like every turn in a conversation, like the end user says something, we want to pull from our vector store, which is very fast, and then get a predetermined answer if we get a hit. If we don't get a hit, you probably want to have some scoring system in place. So if the score is not high enough, that means whatever they said, we don't have a vector for it. So we'll let the LLM just handle it. But this is something that helps speed up the agent and reduces context. So that's one way to make your agent better, and that's something I'm doing. So I use a model from Hugging Face, and I use inference endpoints to have that model live, and then I use Qdrant for my vector store to store all the frequently asked questions and such. Now moving down to here, this is how I manage my prompts. So for voice, I store my prompts in LangFuse, and since I custom coded my agent, either when someone calls the bot or the bot calls someone, we have like a client ID, so it's mapped to this company, and then using that client ID, we just pull the LangFuse prompt for that specific client. And then Firestore is another database from Google. This just stores client details like the business name, the company's email, company's phone number, company's original phone number, and then the company's Twilio number, which is their AI number. So just things like that, data about the actual company, and our code pulls from that as well. So this is where I store that. And then moving on to my actual backend, the server, I use AWS Lambda. This is where I store my endpoints. So whenever someone calls, the AI number, this call endpoint is going to get hit, and then all the setup, like loading the client details, getting the prompts, making sure we're loading up the correct collection from Qdrant for the specific client, because not every client's going to have the same frequently asked questions, and even if they do, they're probably not going to have the same exact answers, predetermined answers that they want for that specific question. So that's what happens on the inbound call. Outbound call goes to this endpoint. I have Make and Zapier here, but I'm slowly migrating over to Go High Level just to handle that automation on that end for form fills. And then also in AWS Lambda, I have another endpoint, which is a queue processor. So let's say if our AI bot calls someone, but they don't pick up, we're probably going to send an SMS. If someone doesn't respond to that SMS, we want to keep polling to see if they respond. And if they don't respond after a certain amount of time, we dispatch another SMS. And then this also helps with things like rate limiting. So in the worst case scenario, if we have a bunch of clients and a whole bunch of people are calling each of those clients, we don't want to get rate limited by either Twilio, or we don't want to overload our LLM, because I am using OpenAI, and you can't just make an unlimited amount of calls or requests in a short amount of time. So we want to prevent that so that none of our clients get any downtime. So there could be delays in high volume situations only by a couple seconds. So that's why we have a queue in place. So that's also connected to my backend. And then Pipechat Cloud, this is what I use to actually deploy the agent, because I custom coded my agent with Pipechat. So it just made sense to use Pipechat Cloud to deploy it. So that's essentially my backend at a higher level. I didn't want to get too technical, but there are other things that could improve the agent. Maybe things like prefetching the availability. So an example would be, someone calls and they're interested in whatever service your client offers. Now they want to book a time with the company. You could just have the LLM make that API call and then get the availability in real time. So that would add some latency. Or when the call starts, you could prefetch the times. So as soon as the call loads up, when all the prompts get loaded up, all the client details get loaded up, that sort of stuff right at the beginning, you could just get the availability then asynchronously. Then you store it somewhere. Now, when you get to the scheduling phase, you can pull from local memory. So you don't have to make that API call when it's time to schedule. You want to make it before, so that way you reduce latency